Hello! Today we're covering a very interesting topic: Anchor account constraints. Solana programs are powerful, especially when they're written with Anchor framework. But they get even better when you stop writing the same account checks by hand. Anchor's account constraints are like built-in security guards for your program. They automatically check things like account, ownership, PDA seeds, signers, token details, and many more, without you having to write a single require macros. But here's the catch: a lot of developers either underuse them or misuse them, leaving programs vulnerable and overly verbose. Did you know there are 18 account constraints in Anchor? Let me guess how many of them you've used. Around 7? Let me know in the comment section if I was right. In this video, we'll break down all the major Anchor account constraints, what they do, when to use them, real-world examples, and gotchas to avoid. Whether you're building a DeFi protocol, NFT logic, or just learning Solana, these constraints will make your programs shorter, safer, and smarter. The signer constraint tells Anchor
this account must have signed the transaction.
It verifies that the account's public key is among the transaction's signers list, meaning the private key holder approved the action. It ensures the user explicitly authorized the transaction with their private key, prevents actions like unauthorized token transfers or sensitive state changes. Its strong sides are: it's secure and simple, prevents spoofing, and works well with multi-sig or delegated signers. Its weak sides are that it doesn't check ownership or role, can be overly permissive if used without validating that the signer has authority over the resource. Best practice is to always combine signer with role verification. For example, checking that the signer matches the state authority or similar field. Common use cases are: ensure only the user can withdraw funds from their own account, initialize or close accounts they control, authorize actions on behalf of a program-owned state, and preventing automation abuse, like someone trying to execute logic without user approval. This ensures only the profile's owner can update it. The mute constraint tells Anchor
this account will be changed during this instruction.
Without it, any attempt to write to the account will fail at runtime with a borrow error. What it does: it marks the account as mutable in the Solana runtime. Anchor inserts the account as writable in the transaction's account meta list. You can modify the account's data or lamports during the instruction. The strong sides are: prevents accidental writes, essential for modifying account data, transferring lamports, or changing ownership, clear intent. Weak sides are: requires the client to mark the account as writable too. Overusing it increases transaction size and compute cost. Best practice is to only use mute when you actually need to write. Avoid making everything mute just in case. Common use cases are: updating user state, for example, scores, balances, profile data, moving lamports between accounts, transferring or burning tokens, closing accounts, and reclaiming rent. Here, both accounts are mutable. User account is closed and its lamports are drained. Receiver must be writable to receive those lamports. The init constraint tells Anchor to create a brand new account during this instruction. It handles allocation, rent exemption, and assignment to the program. What it does: creates a new account with system program create account, sets the program as the account's owner, allocates the specified number of bytes, space, makes the account rent exempt by changing the payer. The required fields are payer, who pays for the account creation, space, how many bytes of storage to allocate, and optional are seeds and bump to derive a PDA. The strong sides are simplifies account creation, automatically verifies the account is not already initialized, and works seamlessly with PDAs. Weak sides that it can only be used once. Initialization must happen in the same instruction. Client must pass the account as a writable signer. Best practice is to use the PDAs for safety and determinism. Make sure space is precisely calculated. Combine with bump to avoid needing to compute it manually on-chain. Common use cases are user registration, creating a fresh profile account, initializing a vault, state or game object, one-time setup of PDA-controlled storage. In this example, a PDA is created to store user data, authority pays the rent and must be mutable, and bump ensures the PDA derivation is safe. The init-if-needed constraint in Anchor combines initialization and read access. It creates the account if it doesn't already exist or loads it if it does. This can reduce friction for end users by avoiding two separate transactions, one to initialize and one to use. Anchor disables this feature for security considerations unless you explicitly opt in by enabling the init-if-needed feature in your Cargo TOML file. Why? Because this flexibility comes with risks. Reinitialization attacks. If someone drains the account's lamports or reassigns its owner to the system program, Anchor will treat it as uninitialized and allow it to be recreated, potentially resetting state or overwriting ownership. Ambiguous state assumptions. Mixing init and init-if-needed for the same account type can cause off-by-one bugs or inconsistent assumption about whether state has been set if the first increment occurs during init. Best practice. Use init-if-needed only if you're okay with the account being recreated or reset in edge cases. Your business logic tolerates both fresh and reused accounts. You don't allow lamport draining or reassignment to the system program. Otherwise, stick with init and enforce one-time initialization explicitly. Let's talk about init-if-needed and init key differences to clarify these two constraints even more. And the key differences of these two constraints are reflected in the table. Before diving deep into the next constraint type, I have to remind you what is a PDA, Program Derived Address. PDA is a special type of account address on Solana that is derived from seeds, program ID, and bump in most of the cases. PDA is owned exclusively by the program. No private key exists for it. It cannot sign directly, but the program acts as its signer via CPI or invoke signed. PDA is deterministic, secure, and exclusive to a program. And the PDA use cases are vault controlled by your program, state associated with the user, authority over token accounts or minting behavior, and program-owned configuration, counters, queues, registers, etc. This PDA can be enforced using the seeds and bump constraints in Anchor. The seeds and bump constraints in Anchor tell you to verify that an account is a PDA derived from specific seeds and bump for your program. This is the main mechanism to securely enforce PDA logic in Anchor. And what it does? It asserts at runtime that the provided account matches the seeds and bump and program ID, prevents spoofing, only accepts the account if it matches the expected PDA derived by your program. Enables program sign-in for this PDA via invoke signed. The strong sides are deterministic verification, security guarantee, works well with init or init-if-needed, and automatic bump handling. The weak sides are complexity, brittle derivation, requires bump. Best practice is to always use seeds and bump for program-owned accounts. Be consistent with seeds ordering and types. Store the bump in the account if you need to regenerate it later. Common use cases are ensuring an account is program-owned and derived deterministically, creating vaults, registries, metadata, or configuration PDAs, requiring CPI calls to sign using invoke signed with the seeds, and protecting state from unauthorized mutation or spoofing. This ensures the vault account is derived from the seeds vault and user key. It is owned and controlled by the program, and only the user associated with it can withdraw. The has-one constraint tells Anka,
This account must have a specific public key stored in its struct, and it must match the provided account's key.
It's used to enforce referential integrity between accounts, for example, ensuring an account is controlled by a particular user. What it does? At runtime, Anka checks that my account authority equals to authority key. If they don't match, the program throws an error. It prevents users from spoofing or hijacking state by passing an unrelated signer. The strong sides are simple and declarative, prevents unauthorized access, great for multi-account validation, safe default. The weak sides are only enforces equality, hard dependency, non-nested path support. Best practice is to combine has-one with signer to enforce both relationship and authorization. Use meaningful names like owner, admin, or authority in your account struct to clarify ownership. Common use cases are verifying that the caller owns or controls a specific account like profile, vault, or config. Protecting state modifications like update, close, or transfer from unauthorized users. Ensuring that an account's authority is passed explicitly and correctly. This ensures the vault account has a field named manager equal to the manager key. The manager must have signed the transaction. No one else can update this vault unless the listed manager. The address constraint tells Anka,
This account must match a specific hard-coded or computed public key exactly.
It's often used to validate fixed PDAs, well-known program accounts, or authority fields that shouldn't change. What it does? At runtime, Anka checks that the account's public key is exactly equal to the provided expression. If not, the transaction fails before the instruction runs. It allows you to enforce fixed accounts relationships that aren't derived dynamically via seeds. The strong sides are it's explicit and precise, great for PDAs, and secure. The weak sides are hard-coded values can be brittle, manual management, no auto-derivation. Best practice is to use the static program accounts, PDA validators, or contract-wide config addresses. Prefer these over seeds if you're computing the address externally and want to ensure consistency. Common use cases are verifying you're interacting with the expected program-owned account, like a config or registry PDA. Restricting actions to known authorities or well-defined accounts. Ensuring cross-program interactions pass in the correct programs, like token program or system program. And here's the example where registry PDA was computed in the handler. This ensures the registry account must exactly match the expected PDA derived from the registry seeds, and prevents any accidental or malicious substitution with a fake account. The owner constraint tells Anchor,
This account must be owned by the program specified in expression.
it's used to enforce that a given account is controlled by a specific program, usually SPL token, a custom program, or a non-system program. What it does? At runtime, Anchor checks that account owner equals to provided owner. This confirms the execution logic or data layout is governed by the target program, like SPL or token program. Prevents someone from passing in a similarly structured but unsafe or spoofed account. The strong sides are security check, essential for CPIs, safe fallback. The weak sides are only checks owner field, doesn't prevent runtime panics, and can be bypassed. Best practice is to use it with account info for lightweight runtime checks when full deserialization isn't needed. Always combine with manual deserialization if you're working with foreign program accounts like SPL token, metadata, etc. Not to rely on this alone to confirm identity. Pair it with address or seeds if determinism is required. The common use cases are verifying a token account belongs to the SPL token program, interfacing with accounts from another custom program, performing checks before CPI calls to avoid misuse or reentrancy. In this example, the program doesn't deserialize the token account, it just checks that it's owned by the SPL token program. This allows flexibility while still ensuring you don't accidentally pass in a non-token account. The executable constraint tells Anchor,
This account must be marked as executable in Solana, meaning it's a deployed program.
it's used when your instruction interacts with another program via CPI, instruction, introspection, etc. And you want to verify that the passed-in account is indeed a valid executable. What it does? At runtime, Anchor checks that account executable equals true. This confirms the account is a deployed Solana program, not just a data or system account. It doesn't check what the program actually is, just that it is flagged executable. The strong sides are protects against spoofing, simple safety check, and lightweight. The weak sides are it doesn't verify program identity, won't prevent logic bugs, and not sufficient alone. The best practice is to always pair with address if you need to ensure the exact expected program is provided. Use it for SPL token program, metaplex programs like token metadata, instruction introspection, for example ED25519 program, custom CPI targets, etc. In this example, the token program must be executable and match the SPL token program ID. This protects against spoofed or invalid CPI targets. The zero constraint tells Anchor,
This account must be uninitialized, meaning all bytes are 0.
it's typically used when you're passing in an existing account already allocated and you want to ensure it hasn't been initialized or used yet, so you can safely initialize it inside your logic. What it does? Anchor checks that the account's data is entirely zeroed out, confirms that the account has not been initialized with any data. Useful for initializing accounts manually, not via init or init-if-needed. The strong sides are it prevents accidental reinitialization or overwriting of live data, Useful when you allocate and fund an account outside the program but want to safely initialize it in the instruction. Plays well with pre-allocated PDAs or externally created accounts. The weak sides are it doesn't allocate or fund the account, runtime cost of checking large account data for all zeros. Anchor gives no automatic guarantee that you will initialize it. That logic is up to you. Best practice is to use this constraint when the account is pre-funded and you want to initialize it manually. You want strict control over when and how initialization happens. Combine it with manual size checks, manual deserialization, or initialization logic, and remember to avoid combining it with init or init-if-needed because they conflict. Common use cases are initializing accounts created via createAccount method in an external script or transaction. Manually initializing a PDA using deterministic seeds outside Anchor's account init flow. Creating a new configuration or state account only once at program bootstrap. In this case, the program expects the state account to exist and be rent exempt. It ensures it hasn't been used before, still all zero. The close constraint tells Anchor,
when this account is closed, its lamports drained and data cleared, send its sol to the specified account.
It ensures safe deallocation and automatic sol transfer to a recipient account, often a refund to the user or treasury. What it does: when your instruction exits successfully, Anchor transfers all lamports from user account to authority, sets user account lamports to 0. This is automatically triggered if the account is marked with close constraint and your instruction completes without error. The strong sides are it eliminates manual lamport draining boilerplate, protects against sol loss or leaks, improves UX as users can reclaim rent when accounts are closed, and encourages proper resource cleanup. The weak sides are only triggers if the instruction succeeds. Destination account must be mutable, rent exempt, and able to receive sol. Anchor will panic if the destination account is not writable or not owned by the system program. Best practice is to always mark both the closed account as mute and the target account, recipient of sol, as mute too. Only close accounts when you no longer need them, for example, cleanup after user exit or migration, or you want to reclaim rent or refund users. Consider pairing with custom event or log to track account closures. Common use cases are closing, temporary user accounts, escrow vaults or sessions, unused PDAs after task completion, or migrated config or state accounts, and refunding users when they delete their profile or position, or DAO treasury when cleanup happens. This ensures the profile account is zeroed and drained. All its lamports are transferred to user, and Anchor handles this automatically at the end of the handler function. The constraint attribute lets you define arbitrary logic that must evaluate to true for the account to be considered valid. It's like saying,
this account must satisfy this custom Rust expression.
What it does: evaluates the expression after deserialization, once the account is loaded and passed. If the expression is false, Anchor throws the specified error, lets you express domain-specific rules, and checks that Anchor doesn't natively enforce. The strong sides are that it's highly flexible, works with all account types. There's a link to the deep dive into Anchor account types in the top corner. Check if you're interested. Ensures only accounts meeting business logic criteria are accepted. Supports custom error messages for clearer debugging and UX. The weak sides are that it doesn't enforce logic at the account level, only on instruction execution. Can be misused for complex logic that belongs in the handler, and can make validation logic harder to follow if overused. Best practice is to keep expressions simple and readable. Avoid embedding multi-step logic. Always pair with clear error code to help with debugging, and use constraint for the rule enforcement, not business logic. And here's a list of the common use cases. Checking that an account has a specific authority or role, is in a valid state, has a valid relationship with another account, and also filtering accounts passed in via CPI or user-supplied multisig wrappers. This ensures the subscription account is active. If not, the user gets a friendly inactive subscription error. No other logic runs unless this passes. The realloc constraint tells Anchor,
Resize this account's data to the new space specified.
It enables dynamic resizing of account storage, growing or shrinking a program account's data during an instruction. What it does: changes the account's data buffer size via Solana realloc, requires that the account is mutable and a pair is specified, must have enough lamports for increased rent. The strong sides are: it enables variable length data structures, useful for features like adding or removing members' metadata or growing buffers, and it's safer than manual reallocation via invoke. The weak sides are: it's expensive, risky if unbounded, shrinking doesn't refund lamports, just reduces accessible bytes. Best practice is to always validate the new size, pre-calculate required size for padding. If reducing size, be careful with truncated state and index out-of-bounds errors. Use realloc 0 equals true if you want to avoid leaving junk data in the new space. This ensures the group account is resized to hold one more member, the authority pays for increased rent, and new bytes are zeroed to avoid garbage data. Common use cases are dynamic data growth, adding and removing members from a list, expanding a text field or config section, and appending history logs or event records. Shrinking after cleanup, for example, pruning unused data, and updating accounts formats during migrations. Anchor framework provides several SPL-specific constraints that validate token-related accounts in a declarative, secure, and readable way. These work for the SPL token program and the associated token program. And I'll cover them as a group, otherwise this video will never end. Strong sides are declarative correctness, security by default, zero boilerplate, ATA safety, readable and expressive. The weak sides are read-only checks, ATA assumption risk, debugging failed constraints can be tricky, and Anchor won't auto-init ATAs. The best practices are to combine SPL constraints with ownership or signature checks. Use token authority even if the user is a signer, because this ensures they control the token account. For ATA logic, prefer the following: to both validate and optionally initialize. Always specify the token program explicitly. The common use cases are safe token transfers, minting new tokens, receiving to an ATA. For the cross-program token operations, always perform this check. These SPL constraints don't replace logic, they validate account structure and ownership. They can be combined with account init, account mute, and account close constraints for full lifecycle management. They work seamlessly with both native token programs and ATAs when used properly. The instruction attribute allows you to pass parameters from the instruction function into the derive accounts macro struct. These parameters can then be used in constraints or custom logic inside the validate function. What it does: allows you to use instruction arguments inside account constraints. Supports any argument passed into the instruction function, for example, U8, string, pubkey, etc. Enable dynamic seeds and bump checks or conditional validation in account struct. The strong sides are dynamic validation, keep state clean, flexible, type safe, and the weak sides are it's purely for validation, there's desync risk, and it's more verbose. Best practices are to use it when your constraint needs instruction time values, like user inputs or computed PDAs. Avoid overloading it. Don't just pass values that could just be derived from accounts. The common use cases are PDA initialization based on instruction arguments, dynamic size allocation based on argument, conditional logic in validate using instruction parameters, enforcing maximum length or format on inputs, multi-seed PDA based on instruction parameters. Anchor account constraints turn low-level boilerplate into clean and declarative logic. From verifying signers to enforcing token mint authority, resizing accounts, closing PDAs, or securing SPL tokens, you now have a full toolkit to write safer programs faster. The more you lean into these constraints, the less error-prone your logic becomes, and the easier it is for others to reason about your code. They're not just sugar, they're safety rails. If this video helped clarify how and why to use anchor constraints, drop a like, share with your fellow Solana devs, and subscribe for more deep dives into smart contracts best practices. Thanks for watching. Bye!